Hello students, let's keep learning as domain analysis module of continuous systems. Hello everyone, we will learn 4.5 below, Laplace reverse transformation. First, let's look at the general form of fs. We've learned about the typical Laplace transformation before, such as step function, exponential function, triangular function, t to the power of m. They are all rational and divided forms. Let's see fs to a rational split form. According to this feature, fs can be equal to as over bs, where ab is the real number, mn is a positive integer. When m is smaller than n, fs is a reasonable and true divide. First, as, bs is decomposited. We will get fs equal to am multiplied s minus z1 bracket, multiply s minus z2 brackets, multiply s minus zm, divide by bn, multiply s minus p1. Multiply s minus p2 all the way to s minus pm. z1, z2, z3, zm is the root of as equal to 0. We call it 0 point of fs. p1, p2, pn is the root of bs equal to 0. We call it pole of fs. Let's look at the three cases of root. First case, the pole of the single-order solid root. This condition, fs is decomposited into as, divided by s minus p2 multiplied s minus pm, where p1 is not equal to p2 and pm. That is, for different real values, the p will be split to get fs equals k1 minus p1 plus k2 divided by s minus p2 until km divided s minus p2. If you can solve k1, k2, k3, km, you can get a partial split expansion form of fs. Look at the second case when the pole is conjugate ray root. At this point, there is s equal to alpha minus j beta in the root, s equal to the form of alpha plus j beta. Then, if fs can expand into k1 divided by s minus alpha minus j beta plus k2 divided s minus alpha plus j beta plus km divided by s minus pm. If you can solve k1, k2, km, then you can expand fs into partial splits. The third form is the form of rerooting. If p1 has reroots, then the formula can be expanded into k1 divided by s minus p1 plus k2, then s minus p1 squared, plus k3 divided by s minus p2, until kn minus 1 divided by s minus pm. If you can solve k1, k2, k3, kn, then you can expand fs into partial splits. The process of reverse transformation. There are three steps in the process of reverse transformation. The first step is to find the pole of fs. The second step is to expand fs into partial splits. The third step is to transform by checking the table of Laplace or by the known Laplace transformation ft. Below, we target single-order real poles, conjugate complex, and reroute three cases to solve reverse transformation. First, look at the single-order real pole inverse transformation. Let's look at the following example. Fs equals 2s squared plus 3s plus 3 divided by s to the power of 3 plus 6s squared plus 6. First, we are going to find out its pole. The pole is a causal decomposition of the denominator. At this time, fs is equal to the square of 2s plus 3s plus 3 divided by s plus 1 times s plus 2 times s plus 3. So you get 3 poles, and then expand it into a partial split form. That is k1 over s plus 1 plus k2 over s plus 2 plus k3 over s plus 3. The key step is how to solve k1, k2, and k3. So how do you solve k1? Let's equal the first two sub-fs to equal. We will get the following step. The way of solving k1 is to multiply both sides of the equation by s1 at the same time, making s equals -1. Then the right side will become k1. It's going to be on the left, divided by s plus 2 times s plus 3. That's 1 on the left. The left is equal to the right, then k1 is equal to 1. Similarly, the same equation is multiplied by s plus 2 at the same time. Make s equal to -2, we will get k2 equals -5. So solve k3 is the equation both sides of the same time multiplied by s plus 3. To make s equal to -3, we will get k3. k3 equals 6. Then fs is equal to 1/10 of as plus s plus 2 points -5 plus s plus 3 points 6. We can solve ft based on this formula. According to e to the power of -alpha t equal to 1 of the s plus alpha, then s plus 1/10 is the e to the power of -t. S plus 1/2 is e to the power of -2t. S plus 1/3 is e to the power of -t. In this way, ft is equal to e to the power of -t. Subtract 5 times e to the power of -2t plus 6 times e to the power of -3t. That is single order real pole. We know how to solve. Let's look at the pole as conjugate complex. How to solve reverse transformation. Let's look at fs equals to as divided by s plus square of alpha plus square of beta. The fraction of the denominator can be obtained by the factor s plus alpha minus j beta times s plus alpha plus j beta. Spread it in parts. Then fs can be written as k1 divided by s plus alpha minus j beta plus k2 divided by s plus alpha plus j beta. Let's solve k1, k2. The solution of k1, k2 is consistent with that of single root. When solving k1, we will multiply on both sides of the equation. Let s equals -alpha plus j beta. We will obtain k1. The solution of k2 is making s plus alpha plus j beta. Multiply the sides of the equation, making s equals -alpha minus j beta. We will obtain this formula. Look at k1, k2. The numerator of k1 is -alpha plus j beta of f1. The numerator of k2 is -alpha minus j beta of f1. The numerator is conjugate. The denominator of k1 is 2jb. The denominator of k2 is -2jb. the denominator is conjugate. According to the mathematical nature, the numerator and denominator are conjugate, so k1, k2 are conjugate, making k1 equal to a plus j beta. Then k2 is a minus j beta. k1, k2 are conjugate. Then ft is equivalent to the reverse of fl1. Then k1 divided by s plus alpha minus j beta plus k2 divided by s plus alpha plus j beta. According to the typical nature of the Laplace transformation, we will obtain e to the power of negative alpha t multiply k1 e to the power of j beta t plus k1 multiply e to the power of j beta t. We will get this formula. And then according to the Euler formula, we will get ft equal to 2e to the power of negative alpha t a cosine beta t subtract b times the sine beta t. This is the value when the pole is conjugate complex. Let's solve fs to equal 2 plus 2 squares plus 2s plus 5 above s inverted value of ft. Let's take fs for partial breakup. We will get plus k1 divided by s plus 1 minus j2 plus k2 s plus 1 plus j2. The solution of k0 is easy. We can solve k0. k0 equal to 7 over 5. The solution of k1 is to multiply both sides of the equation by s plus 1 minus j2 at the same time, making s equal to negative 1 plus j2, solving k1. Because the k1, k2 are conjugate, k2 can be solved. Then we can use the formula we learned earlier. Put a equals 1 over 5, b equals 2 over 5, alpha equals 1, beta equals 2 into the formula. We will get ft. 2 times e to the power of negative t, 1/5 of bracket negative cosine 2t, subtract 2/5 of sine 2t. This result is the inverse transformation of conjugate complexes. Let's look at the rewritten method. Fs equals to the square of s divided by s plus 2 multiplied by s plus 1. Let's look at this case. Let's partially expand it below. The result of the unfolded sides is equal to k1 over s plus 2 plus k2 over s plus 1 plus the square of k3 over s plus 1. We can easily solve k1 and k3. The solution of k1 is to multiply both sides of the equation by s plus 2 at the same time, making s equal to minus 2. We will get k1 equals 4. The solution of k1 is to multiply both sides of the equation by the square of s plus 1, making s equal to minus 1. We will get k3 s equal to 1, k3 equal to 1. The focus is on how to get k2. Next, we will introduce two solutions about how to solve k2. Multiply the sides of the formula given above by the square of s plus 1. We will get the formula. Then derivative of the formula. The right side is equal to 8. Derivative of the left side, we will get this formula, making s equal to negative 1. Finally, the right side is equal to k2, left equal to negative 3. At this point, k2 is negative 3. This approach requires a certain degree of complexity. Next, we will introduce a simple solution of k2. According to the previous formula, we've solved k1 equals 4, k3 equals to 1. then the previous solution would be written into this form: s squared ratio s plus 2 times s plus 1 squared equal s equals 4 plus 2 plus k2 plus 1 plus 1 plus 1 squared this name. As S converges on the full plane, so for any value equation of the above sub S is established. So let's assume that S equals 0. Put S equals 0 into the formula. Then you will get K2 equals -3. This method is simple. This is the solution of K2. After solving K2, then Fs is equal to 4 divided by S plus 2 plus -3 divided by S plus 1 plus 1 divided by S plus 1. Then 4 divided by S plus 2. Its Ft is 4 times e to the power of -2t. -3 divided by S plus 1. Its reverse transformation is -3 e to the power of -t. Then the inverse transformation of s plus 1 squared. We know that the Laplace transformation of t is one of the squares of s. Then the Laplace transformation of t e to the power of -t is 1/10 of a square of s plus 1. So then Ft is equal to 4 times e to the power of -2t minus 3 times e to the power of -t plus t times e to the power of -t. This is the solution when re-root. Let's look the solutions of two special cases. First, when Fs is a false split, the solution is to turn the false split into a true split plus a polynomial. The solution of true split inversion we have talked. Polynomial inverse transformation according to the previous example. Typical Laplace transformation. Here's a case to illustrate the solution. Example 1. Fs is equal to the square of s 3 squares plus 5 times s plus 9s plus 7 divided by the square plus 3s plus 2. First, we will make this false split into a true split. The method of false split into real division can be used by long division. Use a 3 squares plus 5s square plus 9s plus 7 divided by the square of s plus 3s plus 2. First, 2. This becomes s to the power of 3 plus 3s to the power of 2 plus 2s. The reduction of the two type sub decrease is equal to 2 times the square of s plus 7s plus 7. And the quotient back to 2, it is equal to s plus 3. Finally, Fs is equal to s plus 2 plus f1s. f1s equals to s plus 3 divided by the square plus 3s plus 2. f1s is then partially decomposited. It is equal to. Next, we will reverse the fs. The original function corresponding to s is 2. The corresponding original function is the original function of 1 over s plus 2 is we will solve Ft. The final result is plus 2 times e to the power of -t subtract e to the power of -2t epsilon t. This is the false split. Let's look at Fs with e to the power of -s. Non-rational approach. The processing method is e to the power of -s items do not participate in partial split operations. Use the time-shifting nature when solving. Here is a case. E to the power of -2 divided by s to the power of 2 plus 3s plus 2. Let's break it down into, so f 1 as we can write it using partial decomposition. 1 divided by s plus 1 plus negative 1 s plus 2. Its inverse transformation is e to the power of negative t. Epsilon t. How to solve f1s multiplied by e to the power of negative 2s? So how do we calculate depending on the property of the time shifting? The property of time shifting multiplied by epsilon t minus t0 fs multiplied by e to the power of negative st0. t0 is 2, so t minus t0 is t minus 2, making t of ft into t minus 2. We can solve this example. So ft is equal to subtract e to the power of negative 2 times t minus 2. Parenthesis epsilon t minus 2. This is the solution including e to the power of negative s. Okay, that's all. Thank you. Class is over. Thank you for listening.